Hello and welcome to the final lesson in the 4U course. And we're looking at diffraction gratings as our final topic. So today's goal, of course, being able to determine the pattern that develops from a diffraction grating and basically solving problems involving them. That's that apply them to the real world situations. So the first slide here, we're talking about what is a diffraction grating. Diffraction grating is a device used for wave analysis. It consists of a large number of equally spaced parallel slits. All right, so you'll notice I have the arrow continued here because the grating doesn't necessarily stop. I've got 1, 2, 3, 4 slits. You can have up to 10,000, 100,000 slits. It depends on the accuracy of the equipment you're working with and what type of diffraction grating you have in your hand. So how does it work? Well, we have a light source that comes in and strikes your diffraction grating. So here are your incident light rays. They will then pass through the slits and they will strike the screen. And what will happen, because they're equally spaced, what will happen is that you get this pairing up. So this slit will pair up with this slit. Then you'll get this slit pairing with this slit. Then you get this one pairing with this. So what we have essentially is a series of Young's double slit phenomena. So in general, the diffraction grating acts as a series of Young's double slit phenomena. Okay, and a similar pattern will emerge if that's the case. All right. So very, very similar. We're taking some of the concepts that we talked about in the Young's double slit, and we're bringing them kind of forward. All right. Now, I'm not going to go through and develop the formulas with you. A lot of the proofs, if you take a look at them, very, very similar to Young's double slit. They've just been kind of adjusted. So we have, and I'll give you a bit of a legend here. So where it's really only two new terms have been introduced. D is the distance between slits. So that's something you already had in Young's double slit. Between slits. W is the width of the grating. So we don't need to know how wide the grating actually is. And our capital N is your number of slits. Okay, so it's really number W and the N that are the newer concepts in those two equations. So let's talk about intensity here. What I want to do is let's break this into kind of regions. All right, so let's break it into regions. So I'm going to do intensity, relative intensity, and show the resulting intensity diagram. So rather than doing a couple graphs, we're just going to do it on one axis here. So if you have two slits, so it's Young's double slit experiment. We already talked about the intensity just in the previous one with single slit. You know that if we have two slits, the resulting pattern, you saw this in the lab, you get kind of an equally spaced pattern like this. All right, where the intensity relatively low, all right, but that nice equal pattern. What happens if we jump it up to 6 slits? Okay, what happens if we jump it up to 6 slits? If you increase the number of slits that light's passing through, what will happen in the resulting graph is the intensity will increase a little bit, and what you'll find is you start getting fewer peaks. All right, let's see if I can space it out kind of evenly. So evenly topped peaks. And you'll see this, I got a website on there for you. And what happens is it doesn't go down to 0. It kind of gets jumbled up there. And you get an intensity that looks like that. Okay, so the intensity increases, you don't get those dark bands. Now, if we jump it up to 10,000 slits, the difference now becomes you just get peaks that look like this, single lines. No more curved shapes, okay, because it becomes so focused, the intensity on specific points, that you lose that kind of width for a bright band. So that band decreases in width until it gets to the point where it's just a simple series of vertical lines, taking on kind of the shape or the pattern of that diffraction grating. So, a couple of examples with the diffraction gratings. As I said before, I'm gonna try to get out and use the laser with the diffraction grating so you can see the patterns firsthand. So determine the angular position of the first order maxima for violet light. So we got a whole bunch of information. Just got to go through and decode it. So first order maxima tells me n is going to be 1. Violet light doesn't really matter to me the color. I just need to know the wavelength. So we end up with 4.5 times 10 to the negative 7. When using a diffraction grating with 5,400 slits, so that's our number of slits, over 3 centimeters. And that gives me the width from 3 centimeters into meters, 0.03. So that's the information I am given. So I want to find the first order, the angular position. So I'm looking for the angle. All right. So the formula that we have, m lambda equals d sine theta. So I am looking for theta. I don't have d, so that means I need to calculate d. And if you look at that previous page there, those are the two equations that we're really dealing with. And actually, if I recall, we need to convert that m, let's change it to an n to align with how we've been doing the other formulas. All right, it's just the number, the order number. And I know when I wrote it down, I was jumping back and forth. So let's unify it. Let's make sure it's n lambda so it's uniform in all your equations. All right, so I do have to find d first. So I'm going to do it down here. I know d is my width divided by my number of slits, 0.03 divided by 5,400, which would give me 5.56 times 10 to the negative 6 meters. That then allows me to finish the question. N is 1, it's first order. 4.5 times 10 to the negative 7 is my wavelength. D I just calculated. Times 10 to the negative 6 sine theta. Going ahead and using your calculator, you get 4.6 degrees. So what is that a measurement of here? So maybe I'll just kind of help you visualize. So there's my diffraction grating. There's my distance to the screen. Here's my screen. So we're looking for the first order maxima. So we're measuring that angle right there. Okay, so it's the first order, or the first bright spot measured from center line. Okay, so therefore, oops, max occurs at 4.6 degrees. All right, on to the final example. Which maximum occurs closest to the central axis if the diffraction grating used has 1,200 lines, so 12,000 lines or slits. We know the width, 0.025. And we have a situation where we're given a series of information. So A part, second order, so n equals 2, lambda 7.3 times 10 to the negative 7 meters. We're looking at a maxima. So n lambda equals d sine theta. So we know that it is 2 7.3 times 10 to the negative 7. My D needs to be calculated. So we'll do it right here. W over N. So that gives me the 0.025 over 12,000, which is 2.1 times 10 to the negative 6 meters. So I need that information to finish the question I'm working on. 2.1 times 10 to the negative 6 sine theta. And we get theta equal to 44 degrees. So it tells me that the second order, if I put red light through this diffraction grating, then the second order maxima, which would be the second bright spot measured from the central line, will occur at 44 degrees. B part. So we're trying to find which maxima occurs closest. So it's really kind of an A, B, C, D part question. B, same process. So n lambda equals d sine theta. So again, third order violet. 3 violet is 4 times 10 to the negative 7. My D doesn't change. 2.1 times 10 to the negative 6 sine theta. So the violet light, that comes out to be 35 degrees. And finally, second order green. So my N value will be 2. And they've given me the lambda for that. So second order, so that's 2. 5.1 times 10 to the negative 7 equals 2.1 times 10 to the negative 6 sine theta. Calculating that angle is 29 degrees. So I'm going to answer it as a D part here. So which maxima, so we're looking at which one appears or occurs closest to the central. So we see it's actually situation C. It's the smallest angle. So therefore, the second order green light occurs closest to central axes. There you are. So that's it. Diffraction grating is the last topic we're going to officially cover. Good luck on the test. Good luck on the final exam. And as always, an absolute pleasure teaching each and every one of you. I've enjoyed the semester immensely. Good luck on future endeavors, and we'll see you tomorrow still.